Okay. And we know from the question, the compression ratio is 8. Compression ratio is 8. And 8 is V1 by V2, right? Like I said, from V1 compressed to V2, okay, from bottom dead center to top dead center. And this is also VR1 by VR2. So we can figure out the VR2. When we know the VR2, you also check the thermodynamic table, then you can get T2 and U2. Okay. And it's asking the maximum pressure. So the maximum pressure we know is the pressure of second stage, right? Because if you look at the PV, do we have a PV diagram? So we don't have that. So when the pressure you compress, when the auto cycle it compress to the top dead center, the pressure goes to P2, and P2 start when you have a spark plug and you ignite the fuel, and when the combustion starts, you have the P3. So P3 is our maximum pressure, but we keep step by step, we keep working on it and get a get a P3. Okay, and we use the ideal gas law, which we call IGL. So P1 V1 by T1 equal to P2 V2 by T2, right? We know T1 right here, 290 K. T2 right here, 652.4. V1, uh, V1, we only know V1 by V2, so we can do like this. So P2 equal to P1, T2 by T1, V1 by V2. Right? And V1 by V2 is here, which is our compression ratio, 8. So we get P2 equal to 1,799.7 kilopascal. So we know the compression process, we start from 100 kilopascal, okay, which is almost our normal pressure. and we compress to 1,700, or almost 1,800 kilopascal during the compression process, right? Okay, and then we look at the process 2 to 3. So process 2 to 3, right? So process 2 to 3 is the combustion process, which we have the heat transfer. So heat transfer equal to U3 minus U2. The difference of the internal energy is our heat release from combustion, right? So during the combustion process, we release 800 kilojoule per kilogram of heat. Okay, and we know U1 and we know the U2 right here. So we know the U2, so we can calculate U3 equal to 1,275. Then we check the thermodynamic table, we get T3 and VR3. Okay, and then based on the ideal gas law, we use the same skill again. So P3 V3 by T3 equal to P2 V2 by T2. Right. So P3 is equal to P2 by T3 by T2 V2 by V3. Right. And we know the T3 right here. And we know the T2 from here. T2 is right here. Okay. And V2 by V3 All right. I think we mentioned by last time, if you still remember, during the combustion process, right? When the piston goes to the top dead center, right? And then spark plug ignite fuel, we start a combustion process. And this combustion process at very fast, we can consider it as constant volume. Okay, we can consider it as a constant volume. So that is why a lot of combustion experiments, when we are trying to study some, for example, the heat release rate, ignition temperature, or ignition delay, some combustion experimental studies. Okay, we always consider that volume is constant. So if you study some combustion experiment, they might use some constant volume combustion chamber to test, for example, the ignition, something like that, like the ignition delay or ignition temperature, something like that, or heat release rate. So this from P2 to P3, this combustion process, we can consider it as the constant volume process. So constant volume, which means from 2 to 3, the volume is not changing. The ratio is 1, right? So P3 is 4345 kilopascal. So this is the maximum pressure we have during the process. When combustion happens, we generate the pressure. So the pressure P3 is the highest pressure. And then
Sure.
it's asking
I
the
have a
network
question.
output.
Hello.
So the network
Can I ask
output
from the process
is
1 to 2?
QH
You said
minus QL, right? QH is right here, already know. So that is 800 minus QL, right? And we know the QL is U4 minus U1. Okay, so just like here, no, here, just like here, just like here, if you want to have a U4, you gotta know the VR4. You want to have the VR4, okay, you have to follow like this. And this time we look at 3 to 4. Right? So we look at the process 3 to 4. So the compression ratio again is 8, and it's V4 by V3, and that is VR4 by VR3. Okay, and we know VR3, so we can calculate VR4. Right, and then again we can know T4 and U4. So QL is U4 minus U1, right? So U4 is 588.74 minus U1. Let me check. U1 is 206 my 0.91. So that is so the network is QH minus QL. And you want to look at the thermal efficiency. Okay, thermal efficiency. So we divide my network by the QH. So I have 52.3% of thermal efficiency. We have to think about this. The QH right here, it's based on the temperature you burned, the fuel you burned. Okay, you raise the temperature, so based on the fuel you burned. So this QH is based on the gasoline you burned. And we know the gasoline, the heating value of the gasoline, so we can estimate, okay, how much heat release you're going to have. So, so based on the temperature raise, the heating value, and so based on the change of the internal energy. But this is the ideal, like QH. Okay, normally you spend you burn the fuel, you don't get that much energy increase, as well as your network. Okay, because you have the piston moving up and down. Okay, you get some loss of the energy, right? So seriously, you based on this, you don't have that high efficiency, but the ideal thermal efficiency is 52.3. Okay, and then we note the network we calculate here is the mean effective pressure multiplied by the volume change. We know the maximum volume is when the piston is at bottom dead center. The minimum volume is at when the piston is at top dead center. Okay, so it's the mean effective pressure multiplied by V1 minus V2, right? And we can divide we can have V1, and this is V1 by the compression ratio. Okay, so I can take the V1 out. One minus one by compression ratio. And we have to calculate V1 because we know this is equal to what is our network 418.17. Okay. So I want to calculate this. So I need to find V1 because I already know this is compression ratio 8. So V1 is RT1 by P1 based on the ideal gas law, right? P1 V1 equal to RT1. So we can calculate this R is, right, and T divided by P1, 100 kilopascal. Right? Here I don't write the unit, so you figure out the unit by yourself. So we get V1 is 0.832 meter cube by kilogram, right? So we can substitute our V1 to our equation. So we get the mean effective pressure to be 574 kilopascal. Okay, so what does this mean? The mean effective pressure, what does this mean? So this is meaning a constant pressure of 574 kilopascal will produce the same network output as the entire cycle. Okay, which means during the auto cycle, okay, even with during the auto cycle, the network output will be the same as I use the same constant pressure of 574 kilopascal. Use the same pressure, the work is going to be the same. Okay, so that's the mean the physical meaning of the mean effective pressure. Okay, someone is asking a question. May I ask the thermodynamic table? I think we do have one from a local textbook, but I'm afraid the number are different. I think we all follow the thermodynamic table from our thermodynamic textbook. Okay, um, I think the number in thermodynamic textbook we use the same the value from thermodynamic textbook. Okay, if you found the uh, the thermodynamic table from the textbook of internal combustion engine is different from the thermodynamic table from the thermodynamic textbook. Okay, then we all follow the thermodynamic table from the thermodynamic textbook, right? That's one thing. Another thing is uh, if you want to do some exam, okay, we all give the uh, table. I think the uh, Dr. Tong or any lecturers or TAs, I think they can provide the table for you. Okay, so during the exam, midterm exam, final or final exam, if we want to use a table, we'll provide a table during the exam. So don't worry about this. All right, and we still have 20 minutes to the end. So we want to practice example. Okay, here is a class example. An engine cylinder contains 7 times 10 to minus 5 kilogram of fuel with a heat of combustion. So they give you the QC of 45,000 kilojoule per kilogram. The volume V1 at the top dead center is 0.15 times 10 to minus 3, and volume V2 at the bottom dead center is 1.5 times 10 to minus 3. So they already give you the volume, individual volume for V1 and V2 and QH as well. Air fuel ratio is 16.1, and mixture temperature is T1 at the start of the compression is 300 Kelvin. So give you the T1. Modeling the compression and combustion as the ideal gas Otto cycle. So they give you the gamma and CV. What is the maximum temperature T3 and P3, and what is the pressure P1 at the start of compression? So Okay, we continue the class. So the next cycle we are talking about for the our internal combustion engine is the diesel cycle. Okay, so the diesel cycle is designed by Rudolf Diesel in the year of 1890. Okay, the difference of diesel cycle and Otto cycle, or we can say the diesel engine, or we can say the compression ignition engine to the Otto cycle, which we can say the spark ignition engine. Okay, is, or we can say the gasoline engine, is one has the spark and one has no spark. Okay, so diesel cycle has no spark, but has one fuel injector in there. So you spray it was you make the fuel and air. You spread, you automate it, you automate your particle. Okay, you make the fuel and air to mix well, and with the high temperature and high pressure, and you burn it. Okay, and how to burn it when you automate the fuel. Okay, and the liquid the fuel is in the liquid vapor interface. Okay, and when you burn the fuel, there's some other object we call the droplet combustion. But I don't know if we have the chance to talk about this because this is quite out of the scope in this class. Okay, but if we have time, we can talk a little bit about this, the droplet combustion. So basically, it's replace the spark plug with the fuel injector for the diesel engine or diesel cycle. All right. So if you look at the PV diagram, it was from one to two. Process one to two is isentropic, which we have a constant entropy, and then two to three is the was the heat input, and 3 to 4 we have the isentropic process as well, and 4 to 1 it's the heat output. All right, but the difference is during the heat input, this is the constant pressure. See, the pressure is constant, and during the heat output, this is the constant volume process, or constant volume process. Okay. So if you look at the TS diagram, okay, you can see 2 to 3 is a constant pressure process, right? So from 1 to 2 is the constant entropy. 3 to 4 is also constant entropy. They are isentropic process. And 2 to 3 is a constant pressure, and 4 to 1 is a constant volume process. So we have 1 to 2 is the compression process. All right. So in terms of energy equation, it's U2 minus U1 is equal to minus the work one from 1 to 2. Okay. Why we have a negative? We have a negative because when you compress Okay, when the piston is released, when the piston goes down, when the volume is released, when the gas is released, sorry, when the volume is expanded, or volume is expanded, okay, will produce the work, right? But when we are compressed, it's a different direction. So it seems like we're giving the work to compress. So that is negative. We make the work negative term. The entropy equation is S1 minus S2 equal to 0 by T. Supposed to be integrate the entropy by T, but now it's 0 plus 0. So you can say I have a constant entropy, isentropic process, and I have the no heat input. And then 2 to 3 is a combustion process. So U3 minus U2 equal to QH minus the work from 2 to 3. Okay, and we know this heat transfer is sufficient to maintain the constant pressure, So entropy equation 3 minus 2 equal to integrate the QH by T plus 0. And this is an isobaric process, which we call the constant pressure process. C is constant, or you can say constant. Then expansion, U4 minus U3 is, now we still have the negative because it's from 3 to 4. You're looking at the work from 3 to 4, but U4 minus U3, but it's from 3 to 4. So we give the negative term, right? S4 minus S3 equal to 0 by T plus 0. We don't have the heat transfer, and this is the isentropic process. And heat rejection process is U1 minus U4 equal to minus QL. Okay, it's minus the QL. Okay, there's a negative term because if it's 4 to 1, QL is 4 to 1, it's positive. Okay, just different direction. Okay, so this is constant volume for V4 equal to V1 equal to constant. Right. What I'm saying is, if I write U4 minus U1, that is the QL, right? So that's why we give the negative term. The work is done during the combustion process. This is something different from the auto cycle. Okay, the auto cycle, during the auto cycle, the combustion process only input, we only have the QH. We only have the heat input, but during the combustion, for the diesel process, the diesel cycle, all right, during the combustion process, we have the work done. So QH equal to U3 minus U2, right? But we have to add the work of 2 to 3. That is something different from the auto cycle, okay? So that is U3 minus U2 for the work is the P2 minus P2 multiplied by the volume work. The pressure, I increase the pressure, which is the pump. Where I increase the pressure, which is the pump, right? Because the work, I give the work to the pump, so the pump increase the pressure, right? This we call the shaft work. Or we can say the turbine. In the Rankine cycle, the turbine, I I release the pressure. Okay, so I have the work produced. I have the work produced. This we call the shaft work. But boundary work, like we have a piston, the piston move we have a volume change. Based on volume change, we have the work, right? So U plus PV, U plus PV is the enthalpy. So H3 minus H2. So it goes to Cp T3 minus T2, CPdT, right? The QL, there's no work done. So this is CVT4 minus T1, same as the auto cycle. Okay. So there will be a cut-off ratio. Okay, cut-off ratio, which is the ratio of the cylinder volume. Okay, because during the combustion, okay, in the auto cycle, during the combustion, the volume is not changing. So V2 is equal to V3 during the auto cycle. But during the diesel cycle, volume is changing. So this volume change we call the cutoff ratio, which is the ratio, the ratio of the cylinder volume after and before combustion, right? Which is the V3 by V2. Okay, before the combustion is V2, after combustion is V3. The ratio before and after combustion we call the cutoff ratio, all right? And based on the ideal gas law, IGL, ideal gas law, right? So PV equal to RT. Right? And we know this is the constant pressure. The pressure is constant. R is also gets constant, so that is constant. So the ratio of the V specific volume is the ratio of the temperature. So this is equal to T3 by T2. All right. So we know this part is based on the ideal gas law. Okay. So to calculate the efficiency of the diesel cycle, the thermal efficiency of diesel cycle, again, this is the 1 minus QL by QH, right? And it was approximately QL is CVT4 minus T1. And QH is CP T3 minus T2. Okay. And then this part, right? We know that CP by CV is, in some textbook, they call gamma, or it can, they call K as well. Doesn't matter. It could be gamma or K. Okay. We call the ratio of the specific heat, or sometimes specific heat ratio. Okay. They sometimes use gamma, sometimes use K. Okay. Here we can use the K. So 1 minus, sorry, it should be 1 minus. Okay, so 1 minus 1 over K. K, again, is the specific heat ratio, right? And then, so here, I can take the T1 out. So here becomes T4 by T1 minus 1, right? And here, I take the T2 out. So I have T3 by T2 minus 1. Okay, and then here it becomes 1 minus the cutoff ratio. So not cutoff ratio. cutoff ratio. One minus K and sorry, this is the here is a cutoff ratio to the power of K minus 1 by the cutoff ratio minus 1. Multiplied by the K. And this part is the compression ratio, sorry, the compression ratio. 1 minus K. So it's 1 minus the compression ratio to the power of 1 minus K. K is the specific heat ratio. Okay, so the cutoff ratio to the power of K minus 1 divided by the specific ratio multiplied by the cutoff ratio minus 1. Okay, so from here to here, how to derive it? Okay, I want you guys to go home and try to derive it by yourself. Okay, this is quite simple. Try to derive it by yourself. Okay, and I will do this in the next class. But I want you guys to do it by yourself first. Right? Do it by yourself first. Okay, and I will show how to do it in the next class. And we know this part is larger than 1. Sorry, not this part. This part is larger than 1. And compared to Otto cycle, the efficiency of Otto cycle, that is 1 minus the compression ratio to 1 minus K. Okay, so if you compare the efficiency of diesel cycle and efficiency of Otto cycle, the difference is here, this part. And this part is larger than 1. So we can say the efficiency of Otto cycle is larger than the efficiency of diesel cycle. Although we know that in terms of the power, of course, diesel engine is higher than or the gasoline engine yet, that we know in terms of horsepower. But we are talking about the thermal efficiency. The thermal efficiency, in terms of thermal efficiency, the Otto cycle is higher than the diesel cycle. Okay, so once again, this part, okay, this part. So from this part to this part, okay, I want you to derive it by yourself. Okay, I want you to derive by yourself. You work that at home and try to derive it. And the next time, okay, next week, I'll show you how to do it. But I want you to practice by yourself. Okay, someone is raising a hand, but you probably need to type it in the in-call message, the chat box, and I can know your question. Otherwise, you raise 1,000 hands, I don't, yeah, I don't get your question. Okay, so we know this is the Otto cycle is higher than the diesel cycle in terms of the thermal efficiency. So in practice, the diesel engine can operate on a higher compression ratio than SI engine. Okay, diesel engine compared to the gasoline engine, I can operate at higher compression ratio. Why? I think we already talked about this. Okay, so the the gasoline engine based on the Otto cycle, it has a spark plug. So normally we use a spark plug to have the combustion process, right? But we know the gasoline fuel, it will, if you don't have the good octane number, or because it has the limited octane number, so once you burn it, it might, some part of the diesel, the gasoline fuel might burn by itself, might ignite by itself. So there will be two uh, combustion wave, or three or four or five. There will be many, could be many combustion waves. So combustion waves will hit to another combustion waves, which will call the engine knock. So once you have too high compression ratio, the gasoline fuel might have the auto ignition or ignite by itself. Some part of it might ignite by itself or might burn by itself, which will cause the engine knock. So SI engine or gasoline engine, it cannot operate at too high compression ratio. But diesel fuel has no problem with that. Well, higher pressure, okay. And we want a higher Cetane number because we want it to be auto burned. We want it to be auto ignite. So it has no problem of auto ignition. We can say it has no problem with the auto ignition. Even we want it to be auto ignite. So diesel engine can have the higher compression ratio compared to the auto engine, auto cycle. or gas SI engine, we call the gasoline engine. So we can say diesel engine can have the higher compression ratio than the gasoline engine. So diesel engine has the higher uh, power than the the gasoline engine. So SI engine has a limited compression ratio due to the detonation. We call it spark knock. Diesel engine knock is not a problem, so only the air is compressed. Oh, so the student is asking, may I ask you to explain again why the auto cycle has a higher thermal efficiency than the diesel cycle? It's right here, all right? Okay, so because this part, this part is larger than one, so your compression ratio, let me use some different, your compression ratio, no matter what this value is, you're trying to multiply by something higher than 1, and 1 minus something multiplied by something higher than 1. You compare to this. If this is multiplied by something higher than 1, for example, you multiply by 2, something like that. So you will make this value lower than this value. It's quite obvious. So we can say that auto cycle thermal efficiency will be higher than the diesel cycle thermal efficiency. Okay, we can look at one example. An ideal diesel cycle with the air as the working fluid has a compression ratio of 18, cutoff ratio 2. So compression ratio 18 and cutoff ratio 2. At the beginning of the compression process, the working fluid at 100 kilopascal. So I give you the P1, 300K and 1917 volume. Utilizing the cold air standard assumptions, determine the temperature and pressure of the air at the end of each process. The network output thermal efficiency. Once you have a network output, you have the heat input. So that is, you can find the thermal efficiency, the mean effective pressure. So once you have the network output, you have the volume change from V1 to V2, and you have the mean effective pressure, right? So we know the compression ratio is compression ratio is 18, and cutoff ratio is 2. Okay, and compression ratio is V1 by V2. Okay, remember, here I use the capital V. Okay, this is small v, this is capital V. Right? And they give you 1970 centimeter cube. This is the capital. This is a capital V. What is capital V? What is small v? Capital V is this is volume. But if volume, this is the specific volume. The specific volume. But now they give you the pure volume, which we call it. That's why I use the capital V. Okay. If I use a small v, that is the specific volume. Okay, specific volume. Right. So V1 is V1 by V2. So this is 18. Right. And we already have V1. This is our V1, 1917. So I have V2. Right. And also our cutoff ratio is 2. And cutoff ratio is V3 by V2. Right. So once again, the cutoff ratio is the volume change between in the volume change in during the combustion process, which is from V2 to V3. So I already have V2, so V3 is 213 centimeter cube. Right? I think we stop here because it's almost the time. So we can turn off here if you don't have any questions. Right? And next week, which is the October 7th, okay, we'll meet next Monday, 10 o'clock. Right? Thank you for listening. So we stop here. Thank you for listening. If you don't have any questions, okay, you're free to go. Thank you. Bye-bye.